Hi everybody, welcome to Objective 4.2 video notes. So we're going to talk about the properties of ionic compounds and also metallic substances. So in your textbook, you will see these chapters and these sections, and it will really help you learn if you do this kind of stuff. Okay, some definitions. Electronegativity, we already know, is the ability to attract bonded electrons. So if an atom is very electronegative, it'll pull the electrons all the way off another atom, and that's when an ionic bond happens. Once one atom has pulled off electrons from another, it becomes negative, and then the atom that got its electrons pulled away becomes positive, and you get a metal and a non-metal that are ions. So we got a metal ion and a non-metal ion, and then the positives and the negatives attract, and that's an ionic bond. So what kind of properties occur when these substances form? So there's high bond energies because the positives are attracted to negatives. That's a strong attraction, electrostatic force. So usually ionic compounds have high melting points. They're hard and brittle materials. They're those crystals that you saw forming in one of the activities that you did. They're electrical and thermal insulators. They're non-conductive when they're solids because those charged particles are stuck in place. They conduct electricity when they are melted or dissolved because the ions can move, and when charges can move, electricity can flow. So the metal and the non-metal bonded together gives a big electronegativity difference. The electrons go from low electronegativity to higher electronegativity. And now some of the ionic compounds are soluble in water, some are not. Okay, so what holds an ionic compound together? The force of attraction between oppositely charged ions will hold ionic compounds together. How can we test to see if something is ionically bonded? All right, so you can bring down the hammer. Ionic compounds are brittle solids because when they are struck with a hammer or stressed, then positive ions will get put next to other positive ions, negative ions will get put next to negative ions, and they will shatter along those lines. So they make crystals, and those crystals are alternating patterns of positive and negatively charged ions. And when that crystal structure is disturbed and ions with the same charge are pushed next to each other, they will break apart along those lines. Okay, we could check for conductivity for ionic compounds. So if you put ionic compounds into electric current, they will not conduct electricity. Well, they won't complete the circuit because those ions are stuck in place, positive, negative, and they cannot flow. The charge cannot flow. If you start to melt them, all right, then the ions can move and the charge can flow. If you put them into water, they will break apart, and water will surround the positive ions and the negative ions, causing them to dissolve, causing the ionic compound to dissolve, and then the ions can move. So when they're solid, they do not conduct, not as solid, but when they're melted and the ions can move, or when they're dissolved and the ions can move, then they can conduct electricity. All right, that was ionic compounds and their properties. Here are metallic compounds or substances and their properties. So we talked about ionic, and now we're going to talk about a different kind of bonding, a metallic bonding. So think about the shiny metals around you, right? Or things you've seen that are shiny metals and you know are metals. It's just a bunch of metal atoms bonded to other metal atoms. It's not really a compound, right? Then what causes those atoms to stay together is that the positively charged nuclei and inner core electrons are called metal ions, and then the valence electrons are the outer electrons. All of the valence electrons are attracted to all of the cations of the metal atoms. Okay, so you see aluminum +3 charge here and aluminum's core electrons, and then all of this aluminum's valence electrons are moving around, and then this other aluminum atom, all of its valence electrons are moving around, and so every one of the aluminum ions has its valence electrons attracted to the other aluminum ions. This is what we refer to as a sea of electron. Sometimes it's called non-directional covalent bonding because they're all sharing those electrons, but not like in a covalent bond. So when we had carbon bonding to another carbon atom, all right, let me just draw that in here. This is something different, so I'm trying to contrast this with the metallic bonding. Okay, these electrons that the two carbon atoms are sharing are stuck between those two carbon atoms. These electrons that the carbon and hydrogen sharing are stuck in being shared between those carbon and hydrogen atoms. That's a covalent bond that we consider sometimes called directional or stuck in the between those atoms. These metal cations, the positively charged nucleus plus all the core electrons, are sort of sharing all of the valence electrons of all the other aluminum ions. And so they're sharing, but not between two only, but between everyone, so it's non-directional. That's one way metallic bonding is described. The other way is calling these valence electrons a sea of electrons that can move and flow. Okay, so what kind of properties do these metals have because of this type of bonding? They have variable bond strength, which means they could have high and or low melting points, but generally higher than some other things. So maybe lower than some ionic compounds, or maybe some are higher. Definitely higher than a lot of covalent compounds, although there's a few covalent compounds that have higher. So usually pretty strong bonds, usually pretty high melting and boiling points, but then there are others that are kind of low. For instance, mercury is already melted. It's a liquid at room temperature. All right, mercury is a liquid, and so it's already melted before it hits room temperature, and so it would have a lower melting point. Now, what about metals conducting? They can conduct heat and electricity pretty well. So heat and electricity moves through them, which means they're good conductors. They are malleable, meaning you can shape them into different malleable, shapeable, flexible, if you will. You can build, you can make ductile, you can make wires out of them, you can make shapes out of them. They're shiny, and then they're solid at room temperature except for mercury. Okay, so why do metals have these properties? Well, if we use this model of bonding and we have these valence electrons that can move in between all of the metal cations, then they can flow. When you hit them with a hammer, they flow and adjust, so they're malleable. When you run electric current, so malleable, here I could spell that right, malleable. So these valence electrons can adjust. All right, they are conductors because those valence electrons, when you apply electric current, the valence electrons can move through the crystals and they can conduct electricity. Okay. So those are some ways you can describe the malleability and the conductivity because of the bonding in the structure. So comparisons of bonding in this current unit. Ionic bonding, here's some properties. Brittle solid crystals. Repeating pattern of positive and negative charged ions. They do not conduct when they're solid, but they do conduct when dissolved, or when they're conduct when dissolved or when they're melted or as liquid. Okay. How do ionic compounds form? When the electrons get transferred from the thing that turns positive, usually a metal, to the thing that turns negative, usually a non-metal. There's also polyatomic ions involved. Metallic bonding, shiny malleable solids. Their atoms turn into cations, but then their valence electrons can move all over. They do conduct when they're solid. They do not dissolve in water, although some react with water. And their electrons get shared between all of the metal cations. So, hey, now we can compare all three types of bonding that we've learned about: metallic, covalent, and ionic. Okay, so we just got done talking about metallic and ionic. So just to refresh your memory on covalent, all right, so I tried to make it, parallel. So metallic bonding is metals. Covalent bonding is nonmetals. Ionic bonding are metal and nonmetals. What happens to their electrons? Metallic bonding, non-directional valence sea of electrons, sharing electrons for covalent, and transferring electrons for ionic. Metallic bonding conduct as solid and liquid. Covalent only, never conduct. never conduct because the electrons don't move and the charges don't move. And then ionic conduct as liquid or aqueous. Variable melting points. Covalent do have variable melting points. They're the only kind of bonding that can have a low melting point, and ionic bonding usually has highest melting points comparatively. Metallic compounds or substances are insoluble in water. Covalent ones, if they're polar, dissolve in water, and then ionic ones, many are soluble in water. Okay. Variable bond strength, high bond strength, but could have low intermolecular forces, and ionic usually have high bond. Okay, oh look, some pictures for models of bonding. You got your ionic with your positive and negative, right? Metallic, the sea of electrons. Look at it moving, and then here's some properties. Covalent bonding, all these ones down here are covalent. So you got your little molecules like carbon dioxide, nonpolar, small molecules but a little bigger, SF6. Then you got your bigger molecules. Oh, there's some water, sugar. Okay, so you have solids, liquids, gases, all that stuff. All right, so here's a good flow chart to help talk about how the structure relates to the function of some substances. So 3 types of bonding, and then covalent, notice, is broken down into covalent network, where you could have diamonds and other things, sand, quartz. Covalent molecular are smaller molecules, and then there are even bigger molecules. Okay, so you've heard of polymers maybe. Polymers are covalently bonded substances in general that could be flexible, could be rigid, and sometimes the flexibility is based on its structure. Okay. Slime is a polymer that could be made. Slime and other polymers have the ability to move because of their structure. Polymers can be flexible or rigid. They can protect you from fire, flexible, and fire resistant. So this resistant is for fire. And it's because of their structure and their bonding. And compounds, due to their structure, are brittle. Okay, and they don't conduct when they're solid. Network covalent substances have really high melting points and boiling points because it's hard to break up those continual patterns of covalent bonds. And then there's covalent network properties like in graphite. All right, the molecules can slide past each other. So to review, some main ideas that we need to re-emphasize. Metallic bonding models help explain properties of metals. Ionic bonding model explains properties of ionic, and covalent explains properties of covalent. How do you predict which type of bond is present? Think about their properties, think about their electronegativity differences, and think about the atoms involved, and then make sure to use evidence to back up your claims. Okay, that's what we're talking about in 4.2. Hope you enjoyed this. Peace out.